Hi, and welcome to today's class. Today we'll be starting chapter 19, looking at thermodynamics in general. Specifically today we're going to be looking at the second law of thermodynamics and spontaneity and how those things sort of go together. But before we dive into that, let's look back a little bit over the semester. And we've looked at a couple of topics which we will connect to at various places in the chapter and sort of bring us around to sort of overall what we're trying to look at here in this part of the course. So first of all, back in chapter 15, we looked at some kinetics, right? This looked at how fast a reaction goes. And we saw that the kinetics or the speed of a reaction can be affected by things like concentration, temperature, catalyst, right? And we looked at the mechanism. So we looked at the process, right? Kinetics was very much concerned with what was happening during the process of the reaction. And that controlled how fast the reaction could go. In chapters 16, 17, 18, we dove into this concept of equilibrium, right? Which predicts the direction of the reaction, or how far the reaction goes toward products. And we looked at things like the equilibrium expression and the equilibrium constant, which gave us a way to quantitatively look at the extent of this reaction or the position of equilibrium. And now we're going to turn our attention to another aspect of reactions, and that is the thermodynamics. Now, we've looked at this before a little bit back in chapter 7, where we looked at thermochemistry, or specifically heat transfer, or what we came to know as enthalpy, right? And we did calorimetry and these kinds of things to look at the heat movement in and out of the reaction, or what we learned to call the enthalpy change of the reaction. Now, in a bigger picture, thermodynamics are used to predict the spontaneity of a reaction, whether a reaction will spontaneously occur. Now, during this, we'll bring up some other thermodynamic quantities, such as entropy and free energy. Now, you probably want to start to review a little bit enthalpy back in chapter 7. We will mention it, we'll bring it up, we'll use it, but we won't go back and look at the details of that. Now, one other concept that we also looked at back in chapter 7 was the first law of thermodynamics, which we always want to keep in mind. And that essentially says, right, that energy cannot be created or destroyed, right? Conservation of energy. The total energy equals the energy emitted from a system. So if we look at that light bulb, we see that while there's 100 watts of energy coming into it, there must be 100 watts of energy coming out, right? We have to have conservation of energy. Now, in this case, right, we get about 95 watts of that dissipated as heat, and about 5 watts dissipated or emitted as light, right, which is what our goal is, right? But the key here is the conservation, right? Another example is the combustion of gasoline in your car, right? The total energy in this case, the potential energy of our gasoline, right? When it combusts, that energy is converted into various forms of energy, but we have to account for all of it. In that case, that energy comes from the heat dissipated by the combustion and also the energy that goes into moving the vehicle, right, and propelling the car. So that idea of conservation of energy, we don't actually ever create new energy or lose energy. It just moves around from place to place or changes from one form of energy to another form of energy. Another thing that we have observed about energy in our sort of own personal experience is that it likes to spread out. It does not like to stay concentrated. So for example, that morning cup of coffee or tea that you have, right, doesn't stay hot, right? It cools down, right? That energy, that heat in the system spreads out to heat up the cup, to heat up the air, right? But that heat gets dissipated from being confined to the liquid out into the wider surroundings. So this sort of pervasive nature of energy to spread out is something that we will explore as we go through the chapter. And it turns out that this pervasive idea of energy dispersal, this nature's desire to spread out energy, is what ultimately will lead us to determine whether a reaction is what we call spontaneous. Now, one of the big goals of thermodynamics is to predict the spontaneity of a process. Now, all that means is that the process occurs without outside interference, right? So we don't have any energy being added. It's just, it happens. Now, on the opposite, a non-spontaneous process requires energy to occur. So we'll look at that a little bit later at the end of the chapter. So spontaneity is determined by comparing a chemical potential, right? So we'll keep this in mind. This chemical potential is one of the things that we will spend a bulk of the chapter trying to establish. What exactly is this chemical potential? So we're going to compare the chemical potential of the system that predicts the direction of the chemical system. So in other words, we're going to look at how this chemical potential changes. So if the system after the reaction has less potential than it did before the reaction, then that reaction will be spontaneous, right? It'll be what we call thermodynamically favored. So again, we're going to look for a decrease in that chemical potential as an indicator, as our criteria for spontaneity. Now, one thing we have to keep in mind, though, is that spontaneity does not mean fast or slow. So when we look at chemical reactions, we have sort of two ways to talk about whether they're favored or preferred. We can talk about whether they're fast, meaning they're kinetically favored, like we saw back in chapter 15, or if they are thermodynamically favored, meaning they have a reduction in this chemical potential. They're spontaneous. So a spontaneous process is irreversible because there is a net release of chemical potential when it proceeds in that spontaneous direction. And so a reaction can only be spontaneous in one direction. Now, if we think about equilibrium, which we just spend the last 3 chapters talking about, right? An equilibrium system, or a system at equilibrium, is not spontaneous in either direction. It doesn't spontaneously move one way or the other. It's at equilibrium. And so, in an equilibrium system, there's no change in chemical potential. Right? It's at equilibrium. So, again, if a process is spontaneous in one direction, it has to be, quote, non-spontaneous in the opposite direction. So, for example, we can look at the rusting of iron, right? So we have that nice shiny iron, steel wheelbarrow. If we leave it out in the environment, right, it will rust. That is spontaneous. That will occur without us doing anything. Right? The opposite, that rusty wheelbarrow going back to the unrusted wheelbarrow, is non-spontaneous, right? That will not occur without some sort of outside interference. So this elusive chemical potential, right? What is it? Right? That's kind of the idea, right? We want to try to figure out what is this chemical potential. So we can think about mechanical process, right, that we're all familiar with, right? This mechanical potential energy that we know about, right? For example, if we drop something it will spontaneously move down, right? It will fall. Okay? What we see there is we see the potential energy of that system decreases as it moves from higher position to lower position, right? From higher elevation to lower elevation. And that is the direction of spontaneous change, right? So it will spontaneously fall. So if we look at this guy holding this wheelbarrow here, or holding this block, sorry, if he lets go of the rope, the spontaneous direction of change will be for it to fall, right? Because that is lowering the potential energy, right? So when the block hits the ground, it has a lower potential energy than it does when it's raised in the air. So what we're trying to do is come up with the same kind of potential, but not for a mechanical system, but for a chemical system. So what quantity can we use to look at to see the spontaneous direction of change? So for example, we know that sodium chloride will spontaneously dissolve in water, right? So that is the direction of spontaneous change. It doesn't spontaneously come out of solution, right? But it will spontaneously dissolve. But what is this value, this potential that is lower here in the dissolved form, right? Lower and higher up here, right? So the spontaneous direction must coincide with a decrease in this chemical potential, right? That's the bottom line, and that's what we're going to try to establish. I mentioned earlier that we don't want to confuse thermodynamic spontaneity with kinetic spontaneity or kinetic favorability, or something is fast or slow. So just to give an example here, it is thermodynamically favored for diamond to convert to graphite, right? So this reaction to take a diamond, convert it into graphite, is spontaneous, so it's thermodynamically favored. However, it is very kinetically unfavored, right? This is an extremely slow reaction. And so while diamond is constantly turning into graphite, right, we don't notice it because this is occurring on extremely slow basis, right? So thermodynamically favored, kinetically unfavored. And so we have these two aspects of reactions that we look at when we study them as a whole. We looked at kinetics, now we're going to look at how we can think about thermodynamic favorability. Again, just to kind of highlight that, why the difference, right? Well, there's kinetics, right, is associated with the process, right? We look at the activation energy, right? How high is this hump here that we want to look at, right? So we're worried about this middle section of our reaction diagram, right? We study, the intermediates, the mechanism, like all of this stuff in this part. In thermodynamics, right, we only care about what something is in the beginning and what something is in the end, right? We want to see how the chemical potential changes, right, as we go from here to here, right? So there's going to be a chemical potential change here. And that's what we're worried about. We're not worried about how we get from here to here specifically. We're worried about what it is here and what it is here, right? So this goes back to what we saw in chapter 7, in thermodynamics we see a lot of state functions, right? Properties that are only looked at the beginning situation and the end situation, and so we calculate them by taking, final minus initial. We saw this with enthalpy, with delta H back in chapter 7, and we'll see it with other properties that we discover or look at in this chapter. One likely candidate for this chemical potential that we're looking for might be enthalpy, right? Delta H from chapter 7 that we talked about, right? The heat transfer in and out of the reaction. Since we know that spontaneous processes occur, and a lot of spontaneous processes that occur are exothermic, right? Do release heat. It might seem likely that enthalpy would be a criteria for a spontaneous process, or might be the chemical potential that we're looking for. But some spontaneous processes are in fact endothermic, right? They proceed from a system of lower potential energy to a system of higher potential energy. So the question is, how can something that absorbs potential energy yet have a net release of energy? Right? So how can an endothermic process be spontaneous? Well, what that really tells us is there must be something else involved. There must be a more complicated solution than just enthalpy being our chemical potential. Now, let's explore this a little further by looking at a couple examples. So first of all, we'll look at the melting of ice. Now, if we think about the melting of ice, it's an endothermic process, first of all, right? It's a net release, a net absorption of enthalpy, or of heat during the process, but yet it spontaneously melts, right? So you have ice sitting at sitting above 0 degrees, right? It spontaneously melts, but this is an endothermic process. Now, let's look what happens on a molecular level when this melting occurs. So if we think about our solid, right, the molecules are very orderly, right? Very rigid. There's some vibrations, but nothing's really happening. In a liquid, however, right, the molecules have more ability to move, right? Their movement is more disordered, right? They're not as strictly arranged as they are in a solid, right? So we've gone from very orderly to somewhat disorderly. Now, this is something called entropy, right? So this more freedom of motion that we have now, that in liquid molecules things can move, right? They can move past each other, we can flow, right? This increased amount of motion increases the disorder, or what we call the randomness of the system on the molecular level. When systems become more random, energy is released, and we call this energy entropy. So we're going to spend the bulk of the next few sections looking at different ideas around this entropy. But, is melting just a one-off case, right? And of course not. There are other examples. So we can look at the evaporation of water, which is, very similar to the melting, right? We're going from a more orderly phase in a liquid to a more disorderly phase in a gas, where now the molecules are not even connected to each other, right? They can move even more freely. Right? So we go from, again, more ordered to more disordered, or we have an increase in this idea that we call entropy. And one final example that we can look at is salt dissolving in water, right? We go from a very ordered crystal structure in the solid to when it's dissolved, we have a more disorderly array of ions within our solvent of water, right? So we go from ordered to more disorder, or again, an increase in entropy. So we can start to see a pattern here, right? That all of these endothermic processes that are also spontaneous all have an increase in entropy. So perhaps this is the key to unlocking our chemical potential. Now, on a general level, we think about entropy as disorder or randomness, right? But in a more sort of systematic definition, right? Entropy is a thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increases. And entropy is abbreviated by the letter S, and it typically has units of joules per Kelvin or joules per mole Kelvin, right? So it's energy units per temperature. Now, Boltzmann defined this concept mathematically by saying that the entropy was equal to a constant, right? The Boltzmann constant, times the natural log of W, where W is the number of these energy equivalent ways. And to connect back to this order or randomness, right? The more random a system is, the more possible arrangements it has, right? The more energy equivalent ways to arrange it. Now, this leads us into what we know as the second law of thermodynamics, right? Which addresses the idea of nature's sort of pervasive movement toward dispersing energy or to increase randomness, right? So the second law of thermodynamics just states that for any spontaneous process, right, so the entropy of the universe must increase. Now, one key thing that we'll point out here is it's really important that the definition says the entropy of the universe, and we'll get back to that in a minute. So the entropy change in the universe must be greater than 0 for a process to be considered spontaneous. So processes that increase the entropy of the universe occur spontaneous. As I pointed out earlier, like enthalpy, entropy is a state function, or it only depends on the final and the initial conditions to give us the change in entropy for a process. Now, if we take an example here, and our example is the expansion of gas. So, if we imagine this as 4 molecules of gas in a container with this valve here. So we start out initially with this valve closed, and over here we have a vacuum. Now, it's not surprising if I tell you that when we do this, when we open this valve, that we spontaneously see an expansion of the gas from this container to fill up both of the containers, right? It's commonly considered, right, that gases will fill whatever space is available. And so, when this happens, right, we can imagine 3 sort of different possibilities. Now, there are more than 3. We're just going to consider this 3. So, we could consider all of the gas to exist on one side or the other. So if we think about the random movement of these gas molecules back and forth, right, we could imagine a state where all 4 of them are on one side or on the other side. We could also consider a state where the gas is evenly dispersed among both sides. Now, as I mentioned, there are other possibilities like 3 and 1 and so forth, but for this example, we're just going to consider these 3 states. Now, all of these states are equivalent in energy, right? There's the same amount of energy present with the 4 gas molecules here, just how are they distributed? But I think it's not too hard to imagine that for one of these states, there's more possible ways to get the arrangement than for the other ones. So I would surmise to tell you that for these 2 states, A and B, there is one possible arrangement. Right? You either have all 4 on the right, that's one possibility, or for B, there's also the possibility of 4 on the left. There's no other way to get that arrangement. But if you think of state C, right, and we think of these as individual molecules, then there are multiple ways to have 2 and 2. Right? And so if we consider this for a second, right, and label each of these 1, 2, 3, 4, then we can come up with 6 possibilities on how to arrange this. So for state C, there are 6 possible arrangements. For states A and B, there's just 1. So I don't think it takes a lot to consider that there is a higher probability of the gas existing in state C than there is in gas A and B, right? 6 times as high, in fact. So if we come back to it, right, again, there's only one possible arrangement to give us A and B. There are 6 possibilities for the arrangement of state C. Therefore, state C has a higher disorder, right? There is more possible ways for the energy to be arranged, or more dispersal of energy, right? It's dispersed throughout the entire container as opposed to on one side or the other. So, state C has higher entropy than either A or B because it has higher dispersal of energy, more probabilities. Right? In fact, 6 times the probability of having state C than either A or B. Now, it's also true that the change in entropy over this process, right? Remember, we started out with all 4 of them on one side, and we opened the valve, and to go from here to here, right, is an increase in entropy, right? Because the entropy of state C is bigger, the final is bigger than the initial, then delta S is going to be positive. Or in other words, we have an increase in entropy. So what does that tell me? It tells me the gas expansion is spontaneous, right? The second law is obeyed, right? That an increase in entropy of the universe led to a spontaneous process, or because this process results in an increase in entropy of the universe, it is a spontaneous process. Whereas the concentration of the gas staying on one side or the other, would not be a spontaneous process, right? Because it would not result in an increase in the entropy.